Welcome to this first module on HVAC motor basics. By following along with this two-part series, you'll learn a lot about the various types of motors, and you'll learn to identify a motor based on its characteristics. You'll also be able to speak more knowledgeably and to help educate people who are selling and using motors, allowing them to be more successful at their jobs. To guide you through these two courses, and to help you better understand this material, we've asked Daryl Robertson to join us and provide more in-depth explanations of many of these topics. You will be able to list the basic components that make up a motor, differentiate between various motor enclosures, explain what is meant by frame size, and identify different types of motors. In this first section, you'll learn about the various components that work together to make a motor.
The first thing I always talk about when talking about electric motors are the stator laminations. These are thin magnetic grade steel sheets that are stacked together to form the stator core. The next component is the rotor laminations. These are stacked together to form the rotor core. Sometimes we encase the stator in a shell, which is the case construction around the motor. To further that, we will use end brackets, also known as end bells or end shields. And within these end brackets or end shields will be the bearing system. We use two types of bearing systems in HVACR motors. Sleeve bearing components that have a wicking material that puts a thin sheet of oil on the shaft to allow the motor to turn. Or a ball bearing motor. We use these when there are more radial or axial loads against the shaft that help the motor turn without binding up. We also press the windings, also known sometimes as the poles or the coil, through the stator. We attach leads to that to allow power to get to those windings and energize the motor. Through the rotor, we press the shaft, which is what we're driving or putting our drive material on to run in the application. If we put all of these components back together, we end up with a complete motor. Whether it's a C-frame bathroom fan motor through a 200 horsepower motor, those same basic components ring true and will be used throughout this training. The other term we will use is NEMA, the National Electrical Manufacturers Association. This is an organization that helps set standards that we build electric motors to, and when we talk about NEMA standards, those are the standards set by NEMA that electric manufacturers build motors to meet.
This section addresses the various types of motor enclosures. The enclosure you select for an application is based on the environment where the motor is used.
What ultimately kills motors is heat. Motors generate heat and the applications we put them in generate heat. We must dissipate heat from the motor, and we do that with the enclosure, or the case construction, end bells or end brackets of the motor. We take into consideration the environment we're putting the motor into and how we can best dissipate heat. The first type of enclosure is an open air-over or OAO construction. There will typically be holes in the end frames or end shields and in the shell of the motor. This is in a typically clean, dry, dust-free environment, a typical furnace blower motor. The next type is totally enclosed air-over, or TEAO. This motor is completely enclosed, the shell and the end brackets, and is typically in an outdoor condenser fan application. The air-over is the key to this motor. It has to be located directly in the airstream to dissipate heat. The next type of motor is an open drip-proof, or ODP. The NEMA nomenclature states that the motor must be enclosed 0 to 15 degrees on the shell and the end frames of the motor to theoretically allow any light moisture, dust, or dirt to drip off the motor without getting inside of it. But the holes in the shell again help it dissipate heat. The next type of motor is a totally enclosed fan-cooled, or TEFC. This type of motor is really a double shaft motor with a fan on the opposite drive end to help move air over the motor and fan cool the motor. Dusty, dirty, wet environments. Typical application for this motor, light industrial commercial. Totally enclosed non-ventilated motors, or TENV, Again, have an entirely enclosed case construction. However, in this case, there's no airflow directly over the motor. They may be located in small enclosed spaces where there's not a lot of airflow, so we have to build this motor longer to provide more shell size to help dissipate heat. The last type of enclosure we talk about is explosion proof. This type of motor must contain a spark inside the motor to not allow any flammable or combustible materials to explode or catch fire. These type of applications we typically see in paint booths, grain facilities, coal facilities, where any combustible material may be present around the motor.
This section discusses the relationship between a motor's frame size and the diameter of the motor.
The next characteristic we talk about are frame sizes. And I get asked a lot, what does frame size mean? Well, frame size is also set by NEMA. There are smaller than non-NEMA motors, which are motors that are smaller than 42 frame. NEMA does not start until a 42 frame motor or a motor that is 5 inches in diameter. There are a lot of HVACR applications where the motor is smaller than NEMA standard. The next group of motors in frame size is 42, 48, and 56 frame motors that we refer to in the industry as fractional horsepower or FHP motors. 42, 48, and 56 frame motors, the frame size truly tells us where the center of shaft is in an application, so that when I take a motor out of an application and put a motor back in that application, the center of shaft is in the same spot, so that the wheel, blade, or whatever driven doesn't hit the side of the housing. The next group of motors are the larger 143T frame motors that are considered IHP or integral horsepower motors. The reason we break these categories is 42, 48, and 56 frame motors tell us center of shaft in 1/16 of an inch. A 42 frame motor is 42 16ths of an inch, a 48 frame motor is 48 16ths, and a 56 frame is 56 16ths of an inch to center of shaft. By using this calculation, we can determine where the center of shaft is in an application, and most contractors believe that is why we use the diameter of the motor, because the diameter of the motor helps us determine where the center of shaft is. On a 42 frame motor, the typical diameter is 5 inches. A 48 frame motor is about 5 5/8 inches, and a 56 frame is 6.5 inches in diameter. On the larger NEMA T frame motors, 143T and larger, these motors also tell us center of shaft, but no longer in 1/16 of an inch. It's the first 2 digits of the frame size divided by 4. So a 143T frame motor, 14 divided by 4 is 3.5 inches. So we can determine the center of shaft by using that frame size. The third digit in the NEMA T frame motors tells us the distance between the mounting footholes in the bottom of the base. So it is possible to switch frame sizes if you understand where the center of shaft is, and on the T frame motors, a 143T or a 145T frame may be used if the motor is punched for the holes in the bottom of the base.
Now that you understand the different types of enclosures, this section will discuss the various types of motors used in HVAC/R applications.
There are several types of motors we use in HVACR applications. The first type is a shaded pole motor. This motor has one distinct coil or run winding, and there are shading bands or copper bands that are forced through the stator that help fix the rotation of this stator. This is the least efficient motor there is in the HVACR market. A shaded pole motor is between 30 and 35% efficient. The next type is a permanent split capacitor motor or PSC. This type of motor has 2 sets of windings, an auxiliary start winding and a run winding, and both windings are always in the circuit. Thus, this motor becomes twice efficient as a shaded pole motor. Anytime it's possible to take a shaded pole motor out and replace it with a PSC, you should try and do it. This type of motor, how we do that is a 6 amp motor that's shaded pole. We cut the amps in half and replace it with a 3 amp PSC. The next type of motor we talk about are split phase motors. This type of motor also has 2 windings in it, an auxiliary start winding and a run winding. But what makes split phase motors unique is a centrifugal switch. This switch allows the motor to start on the auxiliary winding, which you'll note is a very fine gauge wire. It's designed to slowly come up to speed, and since centrifugal force opens the switch and allows it to go to the run winding. This motor's typical belt drive application allows it not to take off immediately and throw the belt off the line. There are three types of split phase motors. There's the standard split phase, then we have what's called a capacitor start motor. Still has a centrifugal switch, is still a split phase motor, but now we put a capacitor into the start winding of this motor. You typically see a doghouse on top of this with a capacitor inside. It's wired directly into the start winding. This allows for a little greater starting torque and a little more efficiency. The third type of split phase motor is a capacitor start, capacitor run motor. This type of motor, we now have a capacitor in the start circuit and the run winding, and again still have a centrifugal switch. This type of motor should never have a speed control put on it. The most efficient motor in the market is a three-phase motor. These motors have 3 sets of windings that pull on the rotor, making them one of the more efficient motors in the market. One of the easy ways to identify a three-phase motor is the number of leads exiting from the motor, either 9 or 12 wire configuration. These are typically in a commercial application. The final type of motor is an electronically commutated or ECM motor. These type of motors are a permanent magnet DC motor that have a control board that runs the motor. These type of motors are more efficient in HVAC applications and typically a good retrofit upgrade replacement for a permanent split capacitor motor. An original equipment manufacturer OEM ECM motor are typically proprietary on the control board to the programming. Thus, OEM ECM motors typically need to be replaced by an OEM ECM motor.